Thanks for asking. I appreciate that. How are you doing?
I don't feel very good.
Oh, it sounds like you're a little stuffy.
Yeah. But besides that, I'm awesome.
Oh, that's good. My sister has pneumonia.
Oh.
Yeah, so that was, yeah. She doesn't like to take care of herself. She'll just keep working and working and working, and then all of a sudden she gets super sick. I'm like, no, take a break. She doesn't know how to do that. I, on the other hand, know how to take a break. I'm like, no, I ain't doing it. Screw it. Anyway, I've been to a Louisville Bats game. Actually, I think I've been to 2 of them.
I think we talked about that last year.
Yeah.
I'm pretty sure
Yeah.
I wore this hat once because I've only been to one, and it was when I was a little kid. But I'd go to like the Joliet Slammers games.
Oh yeah.
So
yeah, I've not been there, but I know what you're talking about. I've ridden the train to Chicago, and it goes right by the stadium. Yeah, so I know where. I know. Well, at least I know kind of where it is, but it's next to the train track.
yeah.
Cool. Anyway, I guess we should talk more about homomorphisms and isomorphisms. Okay. All right. So remember again that when we're talking about a homomorphism, we're talking about a function. So we've got 2 rings. Let's say R and S are rings. I could have used F again. I don't know why. Usually I use a phi. So I'm going to write a phi instead. The book uses F, which is why I end up writing an F, because my brain is not wired correctly. All right, so the first thing we have is a function. So again, sometimes when you have something that you're purporting as a function, you have, and I've emphasized this I know before, but we'll have to come back to this idea later on. If you define something that you're purporting to be a function, you need to make sure that it's not dependent on how you're representing the input, right? So the prototypical example I give you is that if you have a domain that involves fractions, and you say use the numerator or use the denominator, you might have issues if you have different representations of the same fraction. Okay, so when we have a function, when we have something we purport is a function, we need to make sure that it's a well-defined function. Actually, and when we say it's well-defined, we literally mean it is a function. Okay, well-defined function is pretty redundant. A function implies that you put one thing in, you get one thing out. It's the definition of function. So, in any event, we have a function that goes from R to S. Right now, we're not too worried about being well-defined. That will be a topic that will come up later, though. For a homomorphism part for rings, we need to make sure that if I do phi of A plus B, I get phi of A plus phi of B. And if we do phi of A times B, we have phi of A times phi of B. Both of those properties need to be satisfied. Again, we refer to that as operation preserving. That's the conditions on being a homomorphism. And then that's it. It just has to be a function that preserves the operation. So again, what we think about is, remember that this plus sign really means the addition is taking place in the first ring, then we map it. This plus sign means the operation is taking place in the second ring after we map it. And then likewise with the multiplication. So it doesn't matter if you do the operation first and then map, or map and then do the operation, you get to the same place. That's the operation preserving idea. And that was what the book was talking about with especially with isomorphisms. Really all you're doing is just giving a new label to the exact same thing. We're talking about things being isomorphic. But again, for operation preserving is all you need for homomorphism. And then when we want isomorphisms, when we get the extra conditions, right? So for a monomorphism, is the homomorphism plus injective, plus 1-to-1. Epimorphism, I could spell, is homomorphism plus surjective plus onto. and then these two together is what you have for isomorphism.
What's the one under monomorphism?
It's epimorphism, EPI, yeah. Sometimes people just say morphism for homomorphism, just because it's shorter. All right. So monomorphism is 1-to-1, epimorphism is onto, and then isomorphism is both. Mainly, just making sure that I introduce the words to you. I won't ask you to prove something as a monomorphism. I would say show that it's 1-to-1. I wouldn't say prove something as an epimorphism. I would say show that it's onto, or say injective or surjective. But those words do pop up, so I wanted to make sure that you were aware of them. Okay. In case you see them again. So, in particular, if you're asked to show something is an isomorphism, then you really do have 4 things that you have to prove, in addition to the fact that you need to make sure you have a well-defined function. So you have to show that it's 1-to-1, show that it's onto, and it reserves both operations. So anytime you're asked to do something as an isomorphism, you have 4 things that you have to do. Okay. All right, so let's do another example. Let's see, what do I want to do? Let's let's look at number. What do I want to do? This is number 7 on page 80. So many problems to do. I just was having a hard time figuring out which one I wanted to pick. Okay. All right. So number 7 on page 80. We're gonna let. It says let. We're gonna let R be the real numbers. So under ordinary addition and ordinary scalar. Ordinary addition, ordinary multiplication. I say ordinary addition and scalar multiplication too many times when I teach linear. Okay. Ordinary addition, ordinary multiplication. We're going to let S be the set of all 2x2 matrices, but very special ones. They're going to be diagonal, but also have the same element on the diagonal. And the problem asks us to show that R is isomorphic to S. And a pretty standard notation for rings being isomorphic to one another is to use the same symbol you use for congruence in geometry. An equal sign with a little tilde over the top of it. I know 5 of you are in geometry. So you've probably seen that in geometry. Same thing. Because I was like, not me.
Great. No, actually, that's
okay. You were invited. You could have taken it. You don't need an invitation.
That's turned around at the door.
He tried to come and told me.
No data scientists here. All right. So in this case, when it's asking to show that it's isomorphic, we need to actually create an isomorphism that goes from one to another, right? We actually need to create the function. Okay. So what do you think our function should be here? Well, if I go from R to S, I write it this way, what kind of things am I plugging into phi?
Isn't it just
Real numbers, good. So if I say phi of X, just to use a different letter, that's what I'm plugging in a real number. So I have some phi of X, right? What do we want to come out? Do you think, if I want to show that this is an isomorphism? What thing do you want? What object? 2x2 matrix, and what specific one do you think we should do? Well, it needs to depend on what the X is, right? Oh yeah, well yeah, that part's okay. Yeah, I mean, so what form should this thing take? Yeah, that's which is x times the identity. Yeah. But I think I want the output to be in terms of the input. So my output is a 2x2 matrix. I want to make sure it has that form, right? So I need to make sure that the upper left and lower right have the same value, and the other ones need to be zeros. Again, this is pretty clear that this is well defined, right? Because if I change the input, I change the output. Or sorry, that's not what I mean. That's for 1-to-1. If I change my output, I can't have the same input, right? I only have one representation for the real number. It's going to match to that one particular matrix. So this really is a function. So we need to show 4 things again. We need to show that it's 1-to-1, show that it's onto, and show that it preserves both operations. Again, what's our standard technique for showing the functions 1-to-1?
Assume that's not, right?
Or assume that you have 2 outputs that are the same, right? So let's suppose that I'll call it A00A equals B0. Well, sorry, try that again. Phi of A equals phi of B is what I wanted to show. I was a step ahead of myself. Sorry. I hate making you erase. Then what's phi of A? Good, and phi of B is same thing, right? Just with the B's. Because I got a step ahead of myself when I started. Now again, we're trying to get down to what when we're done? A is equal to B, but since we have matrices equal to each other, what has to be true? If 2 matrices are equal, then what had to be true? For matrices in general, if the 2 matrices are equal, then yeah, all the entries are equal, right? And in particular, what has to be true? A is equal to B. Yeah, exactly. So we must have our A is equal to B. So it's 1-to-1. What's wrong?
I said, then all the components are equal? No.
Oh.
Did
I say no?
No. I said no to myself.
Oh.
How about that? Masana heard that.
Yeah.
You said it. It was correct. Masana looked over at me like,
I just didn't hear you, sorry.
no.
That's funny. All right. So again, start with your outputs being equal. Show that the inputs have to be equal. And since they're equal as matrices, all the entries had to be equal, and then in particular, they had to equal to B. Okay. Onto. What do we have to do for onto?
This one annoys me. I don't remember. Onto annoys me.
Suppose there's an. I guess suppose there's an output finally.
Yeah, that's right. Yeah. Given an output, find the input, right? Given something in the codomain, I need to find something in the domain that maps to it, right? So we'll let A00A be in S. Then in particular, where does A live? Yeah, it's an R, right? And what happens if I take that value and plug it into phi? What do I get?
You get the matrix.
Yep, I get the matrix, which is exactly what we wanted, right? Yeah. All right, then we need to do operation preserving. And again, we have two things that we have to show for operation preserving, right? We need to show it preserves sums and preserves products. And again, you can either do it directly, start with phi of A plus B and get down to phi of A plus phi of B. Or like I said before, you can kind of do that meet in the middle approach. Compute phi of A plus B, compute phi of A plus phi of B, and see that you get the same answer. Either one works. And literally it's personal choice. I usually prefer the go from one to the other, but you can do meet in the middle. That's okay. What is phi of A plus B equal to?
A plus B is 0, 0, A plus B.
Good. And since I need to show that this actually breaks apart over the sum, I probably should break this matrix apart. So how can we rewrite this matrix?
A0, 0, A plus B0, 0, B.
Good. And the first one looks like phi of A, and the second one looks like phi of B. This is exactly what we wanted. Now you do the other one. So you do phi of A times B. What is phi of AB?
AB 0, 0, AB.
Good. And since this is a diagonal matrix, when you multiply one diagonal matrix times another diagonal matrix, remember that from linear, that we really do get another diagonal matrix, right? So it'll split back apart. So this will be, and you can check the arithmetic even if you want, but this will be A0, 0A times B0, 0B, which is phi of A, phi of B. That okay? Let me ask you this. Was there anything that was special about R being a real numbers? Did I use the fact that I had real numbers here anywhere? No. I only used the fact that, as a matter of fact, I just called it a regular R rather than the blackboard bold R. Right? I could have just called it a regular R and just had any old ring and defined this subring of the matrix 2x2 matrices where the entries come from an arbitrary ring, and it's still a true statement. Okay? So there was absolutely nothing special about the fact that I had the real numbers. The only thing we required here was that I had a ring. I had something where the two operations were defined. And it would still work for anything. So anyway, since it satisfied all of these things, we know that these two rings are isomorphic to each other. So we're just writing a conclusion statement there. Not an exceptionally exciting problem. It was kind of a follow your nose problem. Okay, this really does look like it's the exact same thing. I just need to make sure that I formally define my function and then go through all of the necessary pieces to make sure that we really did have a one-to-one onto operation preserving function. That's not the important part of the problem. Now, it is an important part of the problem to get practice for how to do these. The important part of the problem, at least in my mind, is, again, we have R as some ring. Over here, we have S is some subring of 2x2 matrices over where the entries come from R. And what we said was they're isomorphic to each other. What that really means is, thinking about it in a different way, there's a copy of this ring over in this space, or this structure, I should say. There's a copy of R inside of there. Now that may sound weird, and why am I emphasizing that? But you've done this pretty much anytime that you've started learning algebra, and in particular graphing. Okay? What I mean by that is, for example, when you graph, you put an x-axis, you put a y-axis, right? But really what we've got right here, here's a copy of the real numbers, right? There's a copy of the real numbers inside that space. Here's a copy of the real numbers inside that space. You've got other copies of the real numbers in there, right? You've done this ever since you've been doing graphing. You do it when you do three-dimensional graphing, right? There's three different copies, if you will, of the real numbers on the axes, right? Same idea. Okay. So this is just kind of an extension of that same idea. Can I make an identification of some smaller thing inside of a bigger thing? Now, none of you have had topology, but there's a topological thing called embedding, and you put something, its exact same structure, inside something else. That's what an embedding is. That's what we have here with the real numbers. The real numbers are embedded inside the set of ordered pairs of real numbers. The set of ordered pairs of real numbers are embedded inside the set of ordered tuples of real numbers, because you do the xy, the xz, and the yz plane. All right? You've got those embeddings in there. So even though this seemed like, besides the fact that you're practicing doing the proofs, it seemed like maybe who cares about this problem? It's an illustration of this. I'm putting something smaller inside something bigger as an exact copy. And that's where the kind of the isomorphism stuff comes from. Okay? You do it a little bit, when you start making formal things out of other things, you kind of have to worry about this idea of, okay, I have something familiar, and can I stick it inside somewhere else? Anyway, I don't really care that that kind of idea resonates right now, because right now we're just kind of practicing around what's going on. But this is why we care, or at least gives you an example of why we care. Well, at least why I care. You may not care regardless. Okay. That's entirely okay. All right. Let's practice with, let me kind of formalize this embedding idea, if you will. If we take, as an example here, if R is a ring, pardon me, then R is isomorphic to the subring R comma 0, where R is an R, of R cross S for any ring S. Bless you. I mean, this kind of makes sense, right? The way I wrote this. It's like the x-axis, right? I know I wrote a lot of words. Okay. But it's the same idea, right? I'm just taking my ring and I'm sticking it inside the set of ordered pairs, where the first coordinate of the component of your ordered pair comes from the ring that I'm talking about. So if I want to define my function from R to R cross S to be isomorphic to this thing, where do you think I want to map R to? What function do you think we're going to use if I want to map it and be isomorphic to this thing? Well, what kind of an object does it have to be? An ordered pair. To be in this subring, what does the second component of that ordered pair have to be? 0. So what should the first component be? R, yeah, there we go. Okay. We actually refer to this as a special kind of map. This is what's referred to as the inclusion map. Actually, it's not an I. Usually we use a Greek letter iota, which looks like an I, except you don't put a dot on the top of it. A small Greek letter iota. We refer to that as the inclusion map. In particular, there would be two inclusion maps here. I could include R into R cross S. I could also include S into S cross S, right? So if you want to be really specific about which component you're being included into, you might write this as I1 because you're doing the first component, right? So if I wanted to go from S to R cross S and include it, what do you think your map would be for I2? What do you think the output should be for I2 if you want to include S and R cross S?
S.
Which one is the second component, or the S component, the first or the second? The second, so you should use
R-S, or 0S.
there, 0S. Yep, exactly. Yeah, I want to do it the other way around. I want to do 0, S. So notice that the subscript is basically telling you the coordinate that isn't necessarily 0. The rest of them would have to be. So what I mean by that is if you did, say you had R7 included in, say, R1 cross R2 cross R9, just making it up. If I wanted the 7 inclusion map, no dot. Why am I putting a dot? Of R, whatever that R happens to be, then you would do 0s everywhere else except the 7th component. Does that make sense? That's what is included into that piece. All right, that's what an inclusion map is. You also have projection maps. Notice that your inclusion maps are going to be 1-to-1. Hopefully it's pretty obvious that it has to be 1-to-1, right? Especially if you think about it as ordered pairs. Ordered pairs are only equal if their components are equal. If you've got an R, 0 equals say an R1, 0 equals an R2, 0, R1 has to equal R2. So it has to be 1-to-1. So inclusion maps are going to be 1-to-1, so they'll be monomorphisms all the time. There's also an idea of what's referred to as a projection map. So say we go R cross S to R. We use pies to denote projection because we don't have any other use in math for the letter pi. Let's make sure we use it for something else. Why wouldn't we? All right, so we're going to project. And it's not unlike doing projection in physics, right? You project down to a different vector. Same idea, right? In this case, if we think about it as a set of ordered pairs, we'd be projecting down to the x-axis. Well, if you project down to the x-axis, the y-coordinate is always 0, so I might as well just ignore it. And if I project down, then this would be just R in that case. That would be your... We do pi 1 because that's going on to the first component. So same idea. If you wanted pi 2 going to S, what do you think pi 2 of R, S will be? S, yeah, exactly. Hopefully, just like it was obvious that inclusion maps were 1-to-1, it should hopefully be pretty obvious that projection maps are onto, always. So, just to introduce yet another notation, because what else would we do in math besides give you some notations? Okay. If you have a one-to-one function and you want to denote with an arrow that it's one-to-one, so say I had my I1 map going from R to R cross S, and I want to denote that it definitely is one-to-one, you put a little curl on the front of your arrow, and that denotes that it's a one-to-one function. Why putting a little hook on it denotes that it's one-to-one is beyond me, but that is the notation that you'll use for an arrow for something being one-to-one. There also is one for onto. Oops. No, let me draw the arrow second. If I say my pi 1 goes from R cross S to R, you draw your arrow, but you put a double head on it. So the double-headed arrow is onto. So a curl on the front of your arrow denotes a one-to-one function. A double-headed arrow on your arrow means that it's an onto function. But no one ever does a curl and a double-headed arrow, by the way, for a one-to-one and onto. Because why would you? That's crazy.
Hello, D-Tech.
What's that?
I said hello, D-Tech.
You'll find it now. I can't remember what the commands are. I haven't used them in a while. But anyway, won't see those much in here at all. However, they do pop up in courses where you do lots of things that involve homomorphisms. In particular, there's a thing called homological algebra that you would do that in.
That doesn't sound terrifying.
No, not at all, does it? You want some more definitions and some more notations? Take some homological algebra. Oh, I didn't take any, by the way. So, you want to do that. But I did do homology in topology, so. Not that anybody cares, but. I will go off on a little bit tangent. There's a lot of things that people do to put, besides the foundations of math. And what I mean by foundations of math is set theory and symbolic logic. That's foundations of math. So remember the stuff we did in discrete where we played around with truth tables and symbols and those kind of things. That's symbolic. Yeah, I know you did. That's symbolic logic and set theory. That stuff, not exceptionally useful. It's useful, but it's not useful as far as applications go. Everything else, people are trying to get tools put together that help you analyze something else in a different context. Okay. So one of the reasons why we do this stuff with these different types of mappings and creating these different homomorphisms is that, say in topology, where there are applications of topology to data science, there's a whole topological data science field. One of the things you're trying to do with topology is this thing the same thing as this thing? And although that may sound pretty easy, for example, how do I know a circle is the same thing as some knotting in a DNA cell? I don't know if it's still a circle or not, because it might be having all sorts of crossings, or maybe it's just wadded up in a ball, right? I just can't tell. Okay? So topology tries to say, if I've got this thing over here that's nice looking and this thing over here that's not so nice looking, how can I tell whether or not they're the same or not? So one of the ways they do that is by looking at these different types of structures, either mappings or groups or those kind of things, to say, well, this one has this property, this one doesn't, so they are different. And we've already talked a little bit about that with isomorphism, right? This one has this property, this one didn't, so they can't be isomorphic. Okay. That's why we put a lot of these things together. Really what we're doing is we're trying to get tools in one language to help us analyze a different language. Okay. Now, whether or not you ever use it later on, that concept is the same, right? Why do you think Newton invented physics? Right? It was to try to analyze the world around him. Okay. So that's what we're doing with all of these things. We're just trying to, is this going to be helpful for something else? Maybe not. But there's very few things in math that have been done that somebody didn't find an application for later. Right? I guarantee you that Euclid did not study prime numbers so that credit cards could be secure on the internet.
He knew.
He knew. He was way ahead of his time. Okay? So I know this stuff may not be the most exciting, and maybe you won't ever do it again, but that same concept of, I want to try to use this thing to analyze something else will come up again. Okay. So anyway, I know I went off on a little bit of a tangent, but I'm in a math class. I'm allowed to do that. Okay. And yes, I know I made that joke before.
You gotta be wearing the shirt when you say it.
Yeah, I should have been wearing the shirt today. I should have. That's right. Well, if I would have things more planned out to the minute, I would have thought about doing that. But all right. Anyway, let's go back to that idea of, can we check if something is isomorphic or not? So this is actually number 35 on page 83. And I wrote number 83 because I started to say 83. All right. So there are 6 different pairs that they give you and ask, why is the first one not isomorphic to the second one? Okay. So remember, I'm going to write this differently. They wrote E in the book. I'm going to write it as 2Z. Remember that isomorphic literally means what property is true in the first ring must be true in the second ring and vice versa. Okay? So again, if one is commutative, the other has to be commutative. If one has identity, the other has to have identity. All right? All of those things. Okay? So 2Z again is our set of evens. And then Z is just the integers. Why are those not isomorphic? In particular, in this case, what does the second one have that the first one doesn't? Was that? Odd numbers, true. True. I would agree with you that there are odd numbers in the second one that the first one doesn't. Okay. Unfortunately, but they're both infinite sets, right? So the size argument doesn't work very well here because they both are. Have you talked about countable sets before versus uncountable sets? They talk about in history,
I've talked about it in some class.
It sounds familiar.
Yeah.
Okay. So countable numbers are literally like you can count 1, 2, 3, 4. Uncountable is like the reals, you can't count them, right? Okay. Anyway, these are both countably infinite because I can do 1, 2, 3, 4, 5. I can do 2, 4, 6, 8, 10. I can literally count them off, right? Put them in a list. But the real numbers you can't put in a list because no matter how you try to list them, there's something that's not in your list. Have you seen that argument before? The diagonal argument? Oh, well, we're going to do a side note because that's kind of fun. We'll do this on the board.
It sounds familiar, but I don't remember.
So it's just a brief thing of how the real numbers are uncountable. That's all right. It's a good little discussion. All right. Again, countable means I can put them in a list. Technically, it means there's a one-to-one and onto function between the list and the positive integers because that's how we count, right? 1, 2, 3, 4. Okay. All right. So let's say your real numbers are countable. This is the argument. And this is not a bad side note because this is something every math major should see, this particular argument. Okay. All right. So say I've got a list. Actually, what I'm doing is if the real numbers can be listed, the numbers between 0 and 1 can be listed. Okay. So here I've just got decimal expansion where I've listed out the real numbers, theoretically. Our idea here is to construct a number, no matter how I make my list, I can always construct a number that's not in the list. Okay? So I can tell that two decimals aren't equal if I have a decimal place where they disagree, right? This is why it's called the diagonal argument. Look down this thing here. Okay? If I want to create a new number, can I pick something that's different than the first digit here? Yeah, sure. This is somewhere with 0 through 9. Pick something that's not 0, not 9, and not equal to that number. I want to make sure I don't use zeros or nines. Infinitely repeating zeros don't give me a new number. Infinitely repeating nines also don't give me a new number. Okay. Anyway, so I can pick my B1 to be different than this. I can create my B2 to be different than that, and not 0 and not 9. Do the same thing here. And so then it differs from everything in the list at every decimal place. So no matter how I make a list, I can create a new number that's not in my list. And so that's what's referred to as the diagonal argument. It shows that you cannot list out the real numbers, so they are uncountable. Does that look like a familiar thing? Yeah. Yeah, there you go. Okay. I knew it was in there somewhere. But anyway, that's what the diagonal argument is. All right. Anyway, back to that. That doesn't help me here because they do have the same size. They are both countable, right? I can think about list them off. 1, 2, 3, 4, and so on. 2, 4, 6, 8, and so on. There is a 1-to-1 onto function between the two of them. But again, so I ask, besides the fact that one has odd numbers and one doesn't, that really wasn't a tangent. That was kind of important to talk about this. That would give me the argument, by the way, that the integers aren't isomorphic to the reals. The integers are countable, the reals are uncountable, so they don't have the same size.
Multiplication is not preserved, right?
What do you mean?
I mean, in 2z, if you moved anything in z to 2z, double it. So when you I need to do this on paper first to make sure.
I think I know what you're saying. If you did your map as this, then that doesn't preserve multiplication. I agree with you that. But is that enough to show that they're not isomorphic because that one function didn't work? No, right? So that particular function is not operation preserving, right? Because phi of xy would be 2xy. Phi of x, phi of y would be 4xy, right? So it's 2x times 2y. So that function's not an isomorphism. But it's not enough to show that they're not isomorphic, right? That's why I said just because one function doesn't work doesn't mean another one might. But there is something that z has that 2z does not. Yeah, there we go. Multiplicative identity, right? Z has a multiplicative identity and 2z doesn't, right? That's it. And that's exactly the difference. So z has a multiplicative identity and 2z does not. Cool, good. Don't know why they made this one so crazy, but that's okay. Oh, I know why. Duh. Never mind. The second pair is ring 1 is R cross R cross R cross R. Second ring is 2 by 2 matrices of with real components, real entries. For a second there, I said I don't know why they made the first ring so crazy, but then I'm like, oh yeah, duh. Now I know why. How many components does your ordered tuple have in the first ring? 4. How many entries does a 2 by 2 matrix have? 4. So I was trying to make you think, okay, well maybe I take the first one and match it with the 1-1 entry. The second one match it with the 1-2 entry. The third one match it with the 2-1 entry. The fourth one match it with the 2-2 entry, right? I mean, that's the matching. Okay. That definitely gives you a 1-to-1 and onto function, by the way. Okay. That phi of x equals 2x gives you a 1-to-1 and onto function in the previous example. Okay. So again, this is what I think this is trying to do in this particular problem and one of the reasons why I'm going through it, just because we have a one-to-one and onto function does not mean we have an isomorphism. Okay. And I'm going to go back to that first example here in a second. So to illustrate something else, but why are these two rings not isomorphic? So again, what we have to think about structure. Since we have 2 by 2 matrices in the second ring, I'll try to ask this without giving it away. When I said that if you want a prototypical example of some type of ring, you should think matrix rings. And what was that prototypical example of that type that I was trying to think of? Yeah, multiplication is not commutative, right? So in the second ring is not commutative. What about the first one? Is that one commutative? Yeah, because all we do for the multiplication is that it takes place in each component, right? So this one is the first ring is commutative, and the second one is not. But I do want to go back to both of these examples, and then we'll talk about the next ones, which are a little bit more complicated, maybe. Well, the last two are a little bit more complicated. This function that we came up with for z and 2z, this one right here, did not preserve multiplication. But does it preserve addition? Yeah, sure does, right? Because the 2 would just distribute over the x plus y. It would be okay. So, I've already mentioned this word. We haven't gotten there yet. But we have, for rings, we have the addition part and the multiplication part. The addition part is what we refer to as a group part. And it's a group under addition. This preserves addition. So z and 2z are isomorphic in some sense. They're isomorphic as groups, but they're not isomorphic as rings. So depending on what type of structure you're talking about, it does have similar structure as far as up until addition, but not for multiplication. Same idea here. These two are isomorphic under addition as groups, but they're not isomorphic under multiplication as rings. Think about why their additive structures are the same. In this first ring, we add component-wise. In the second ring, we add entry-wise, which is the same, right? We just wrote our components. Instead of writing our components horizontally, we wrote them in a square. But it's the same same addition. It's just the multiplication which is defined differently. So they do have similar structures all the way through, they have same structure all the way through addition, just not multiplication. So this is a concept we'll come back to later when we get talking about groups. All right. The next two hopefully are fairly straightforward because we've already mentioned it. These are both the same ring, why they're not isomorphic. The first one says Z4 cross Z14 and Z16, and that second one says Q and R. These are both the same reason why they're not isomorphic. How many elements does Z4 cross Z14 have?
Oh wait, no, because
Yeah, that's okay. How many does it have instead? Instead of addition, you want to. That's more than
56.
56, yeah. You multiply them, right? 4 times 14. The second ring has 16 elements in it. Okay. So they don't have the same size, so they can't have the same structure if they don't have the same size. Okay. The other part, and I know this is something that came up in discrete, but just generally speaking, for finite sets, they literally have to have the same number of elements in them to be one-to-one onto. And in fact, for finite sets, one-to-one implies onto and vice versa. That's not true for infinite sets, but for finite sets, one-to-one implies onto implies one-to-one. So for C, they don't have the same size. D, they also don't have the same size. One's countable and one's uncountable. The rationals are countable. Do we know why they're countable? Yeah, the integers are countable, and you can do the rationals as ordered pairs of integers, and then a little bit of a relation idea. But the idea, I like this one idea of why the integers cross the integers are countable. We'll just do the positives. So let's just look at all the points in the plane that have integer coordinates. The lattice, they're called lattice points. So if I want to show that this set is countable, I need a one-to-one and onto function from the integers to this set. Okay. But this one's more of a proof by pictures, if you will. And the idea is follow this line like I'm doing here. So go over, diagonal up, diagonal down, go over, diagonal up, diagonal down, and keep repeating that pattern. And then you can see what the one-to-one and onto function has to be, because this is how I'm counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's my counting. That's my one-to-one and onto function from the integers to the integers cross integers. I like playing with those kind of things. But anyway, there's a whole thing of some people do things that are called proof without words. This is kind of the proof without words idea. Just draw a picture. Here's what it's supposed to look like. You don't get away with it.
That. Proof without words.
Proof without words?
Yeah. No. Next exam, I don't know an answer. This was a proof
without words. All right. So both of these, the reason is the rings don't have the same size. Oops. And remember, there was a fancy word for size we used in discrete. Cardinality. Cardinality is the size of a set, and we use that word, especially when we have infinite cardinality. And there is a whole subset of set theory that talks about infinite cardinals.
Birds as far as the eye can see.
Birds, that's kind of funny you say that, because Dr. Stickles is home today. She sent me pictures. We had like 500 blackbirds in the yard. It was just birds everywhere.
That's terrible.
I know, exactly.
Oh my gosh, I forgot about that. I will never forget about it.
What's
Every
that?
time I see an American film, what is it? Is it birds?
Yeah, the birds.
The birds,
Yeah. Hitchcock?
Yeah. He had to watch that film. But it was,
That's right.
yeah. And now I can't look at birds to say.
You come around to my house up on the lake, we see all sorts of birds. We see pelicans. We got pelicans on the lake right now, too.
Wow.
It's kind of fun. We're in the migratory pattern. They're huge. Holy cow.
I like birds. They're
Yeah.
pretty, but they're scary. And
Yeah.
I think that movie made them scary for me.
Yeah.
Because I've never thought birds were scary until I watched that.
There are two more in here. Let's see. E has these will require a little bit more effort. But both of these are similar as to Y. Let's actually do F before we do E. I'm only doing it in that order because it's what it has in the book, but let's do F before we do E. Remember again, if they're going to be isomorphic, then they have to be isomorphic. They have to have absolutely every single structure idea being the set. If one has identity, the other has identity. The one's commutative, the other is commutative. If one has characteristic n, the other one has to have characteristic n. That's another idea. That would have to be exactly the same. Okay. So remember, characteristic again is how many times, what's the minimum number that you have to add each element to itself that many times to get back to 0, right? And we said all we really need to do is check 1, and that gives you the same thing, okay? In Z16, how many times do you have to add 1 to itself to get back to 0? 16, right? Because I have to get up to 16, correct? So Z16 has characteristic 16. Looking at the other ring, the identity there is 1, 1. How many times do you have to add that identity to itself to get back to 0, 0? 4. So the first ring has characteristic 4. The second ring has that characteristic 16. So that's why, oops, it's an R. The first ring has characteristic 4. The second ring has characteristic 16. I can't do the same thing with part E because both of them have characteristic 0. There is no n that satisfies n times 1 gives you 0, right? If I add 1 to itself, I can do it infinitely many times in the integers. I can do it also infinitely many times in Z cross Z2 because I'll never get back to 0. Now the second component will flip back and forth between 0 and 1. But the first component will never get back to 0. So I can't use the characteristic argument there. However, think about it another way. If I don't use 0, can you ever add an integer to itself enough times and get back to 0? No, right? Any integer I add to itself over and over again is either going to go off to positive infinity or negative infinity, besides 0. Can you find something in Z cross Z2 that you can add to itself a certain number of times and get back to 0, 0? 0, 1 will work, right? So 0, 1 plus 0, 1 is 0, 0. So there is an element in here that will add to itself and give you 0, but no element of Z adds to itself. I should say added to itself. Gives you 0. We're going to talk about this later, so I'm going to go ahead and mention it now. You don't need to write this down. In a group, so in this additive part, in a group, the minimum number of times that you operate an element with itself and get back to the additive identity is called the order of the element. Okay? So in this case, the element 0, 1 would have order 2. Because I added it to itself. I needed 2 copies of itself to add together to give me 0. Okay. So in that case, it has finite order because it's 2, right? It's a non-zero element with finite order. There are no non-zero elements in Z that have finite order. Okay. So I just wanted to give you that word because we're going to come back to that word. So go ahead and introduce it now since we've been talking about adding something to itself that many times. Okay. Anyway, so those are the kinds of things that you're looking for when you want to talk about structures that are not isomorphic, something that one has that the other doesn't. Okay. So I like this as a concept for a problem on an exam, by the way. Yeah, it gives you the idea of the concept without having to go through a whole bunch of function things. So it's another reason why I'm emphasizing this type of problem because you can probably see this again. Probably more than once. Okay. All right. Any questions on that one at all? No. Want to do another one? Sure. Why not? This is number 12 on page 81. This one's asking if the following functions are homomorphisms. So just do they preserve both operations? Okay. So part A, your function goes from z to z. Where phi of x is negative x. Again, the directions are, is it a homomorphism? So all you're being asked to do in these problems is check whether or not it's operation preserved. Now, just as a hint here, there's nothing special about that being the opposite of x. I could use any integer I wanted in the same place and you get the same answer. So what operation is it not going to preserve? It's not going to preserve multiplication, right? Just like it didn't preserve multiplication here. Because what happens when you try to split the multiplication apart? Well, whatever the coefficient is in front of the x gets multiplied by itself, right? Do you agree with that? Okay. Does it preserve addition, though? Yeah, sure does. Yep, it preserves addition, right? There's not any issues with addition. Because the same reason why we talked about up there, if you do x plus y, that constant would just distribute over the x plus y, right? So there's no issues with addition. It's going to be the multiplication that causes the problem. Okay. So this would preserve addition, does not preserve multiplication. You should be able to check that without too much difficulty, I would think. What about the exact same function but change the ring? Rather than going from z to z, go from z2 to z2 to z2. And rather than actually trying to prove it directly, let's see if we can simplify this instead. Z2 means we're doing things mod 2, right? So I'm doing things mod 2, and not worrying about whether or not I have 0, 1. If I do x plus x in Z2, what do you get? No matter what the x is. If I do x plus x in Z2, what do I get?
0.
You get 0, right? So if x plus x is 0, what's negative x equal to?
0.
X equals x, right? If my x plus x is 0, then x and negative x are the exact same thing, right? It's its own inverse, additive inverse. Okay. I mean, it's not too hard to check with Z2 that you've got 0 plus 0 is 0, 1 plus 1 is 0. But this would be true for any element. When you add it to itself, you get 0. So for example, in Z4, 2 and negative 2 are the same thing. In Z8, 4 and negative 4 are the same thing. Okay. Does that make sense? In Z2 cross Z2, everything is its own inverse. 1, 0, 0, 1, 1, 1, 0, 0, they're all their own inverse. So anyway, going back to this, which is where we started. If phi of x equals negative x, but you're going to Z2, what function do you really have? How can I simplify the output? You can just get rid of the negative. Everything's its own inverse in Z2, right? So this is really, since we're in Z2, this is just really the same thing as x. So phi of x equals x, that's the identity map. Does the identity map preserve addition and multiplication? Sure. So that one is a homomorphism. let's talk about Power Rangers.
Mighty Morphin.
Okay, that was funny. Oh, shoot. Rationals to rationals defined by 1 over phi of x is 1 over x squared plus 1. Does that look like something that's going to have any hope of preserving either of the operations? No. And this one, I would probably just do a specific example. I would probably do, to show that it does not work over, say, it doesn't preserve addition. Phi of 1 is a half, right? So phi of 1 plus phi of 1 would give me, well, that's actually, no, sorry, that's for
Multiplication doesn't work.
Well, phi of 1 plus phi of 1, phi of 1 plus phi of 1 would be 1, but phi of 2 is not 1. Phi of 2 is a fifth. So it doesn't break up over addition either, right? And if we do, say phi of 1 times phi of 2, you would get a tenth, right? Phi of 1 times phi of 2 would be a tenth because it would be a half times a fifth. But phi of 1 times 2 is just phi of 2, which is a fifth. So that wouldn't work either. I would just pick specific examples to show that doesn't work for that one, rather than trying to do something with doing it with yes, exactly. Thank you. My brain died. I don't know what the problem was. I couldn't get the word symbol out. That was what I was trying to work with, get the word symbol out. All right. There's a couple other ones in there. B. Phi goes from R to matrices. It's actually 2 by 2 matrices with real coefficients, where phi of x is negative x 0, x 0. If such a thing is going to fail, looking just specifically about what you know about matrices, do you think you're going to have a problem with the addition, or do you think you're going to have a problem with multiplication? Probably the multiplication. If there's going to be a problem, it's probably going to be with the multiplication, right? Because when you add matrices, they behave nicely. It's when you multiply matrices when they don't behave nicely, right? Okay. So let's just do something specific again. Maybe we do, let's say we have phi of 1 times phi of 2, and then phi of 1 times 2. Again, just make something easy. I don't know if it works or not. I haven't really thought through it. If you don't know, and this is pretty good advice anytime that you're trying to do things in math, especially when you're trying to do proofs. Create examples. And that's a hard thing to do sometimes, but creating examples can see if there's a pattern or not. Okay? In particular, if I find an example that doesn't work, I'm done. But if I do like 3 or 4 examples and it works every time, then maybe I should bother trying to prove it. Okay? So if you don't know where else to start, just try some examples and see what happens. Okay? I can't give any better advice than that. Unfortunately, there's no hard and fast rule that works for everything. Okay. All right. So if phi of 1 times phi of 2, I would have negative 1, 0, 1, 0 times 2, 0, negative 2, 0, 2, 0. Ooh. What do we get?
-2,
Okay. The reason why I used 1 again, by the way, is because it was easier to simplify the upper one, because now it's just phi of 2. What is phi of 2 equal to?
-202.
And are these two things the same? No. So it doesn't preserve multiplication. So it's not a homomorphism. Does that make sense? Okay. All right. Since we only have a few more minutes, let me. There's a couple of things that I want you to do for homework. I want to make sure that we know what the definitions are. So, one of them is, I'm going to actually define 2 things. I don't know if they're all in the homework, but this one in particular is, if we let A be an element of a ring, we say A is an idempotent of R if A squared is itself. We may have talked about that particular word because I may have defined it in linear as well. But anything that squares to itself is called an idempotent.
I don't recognize that one from linear.
Okay.
I do. I don't remember. I didn't remember it in there, but like
Yeah.
I know I've seen it.
Yeah, okay. But anyway, if it's this was on your test though. If you're in an integral domain, what are your only 2 idempotents? This was on your test.
0 and 8.
0, the multiplicative identity, right? 0 and 1, right? If you have an integral domain, the only idempotents are 0 and 1. Okay. Those are referred to as the trivial idempotents because in every ring, 0 squared is 0 and 1 squared is 1. Okay, so those are the trivial ones. So if you're interested in idempotents in general, then you're looking for non-trivial idempotents. Okay. In any event, that's a definition that pops up. Another one that might pop up at some point is the idea of what's referred to as a nilpotent.
We definitely talked about that.
Yeah. Oops. So a nilpotent element is that there's some power of A that gives you 0. So if I write Z plus, I mean the positive integers. That's what the Z plus means. So nilpotent. Potent is the power, right? That's where the potent comes from. So you're talking about power. So idempotent is the squaring to itself. Nilpotent is power gives you 0. One of the interesting things about nilpotents, if you're in rings of identity, is that you can create units out of them. What do I mean by that? Well, certainly if something is a nilpotent, it's a 0 divisor, right? Just A times A to the n minus 1 will give you 0, so it's a 0 divisor. And we know that 0 divisors can't be units. However, we can create units from nilpotents in the following way. If you multiply 1 minus A times that sum, and this should look familiar for a geometric series, for example. Your factoring formulas for difference of cubes, difference of cubes. This actually gives you a factorization of anything. Notice that when you distribute the 1 through, you just get this back again. You get 1 plus A squared up to A to the n minus 1. What do you get when you distribute the minus A through?
Everything, but adds a top term.
Yeah, puts a minus A to the n on the end, right? So you get 1 minus A to the n. By the way, this shows how to factor x to the n minus y to the n all the time. Your difference of cubes formula is a special case of this. Okay. In particular, if a is nilpotent, so I know that a to the n is 0, what do we end up with at the end? If a to the n is 0, then we just end up with 1. Yeah. So this is what I mean by that you can create units. If a is a nilpotent, then 1 minus a is always a unit. Because I found something to multiply by it to give me 1. So there's, in some sense, some connections between nilpotents and units. Now you don't necessarily create all units in this fashion, but if I have nilpotents, I can create units out of them. So anyway, just wanted to play with that a little bit. Let me give you some problems to work on because I knew you were dying to do that, right? This is page 80. What did I have? 3 and 10. 10 involves this idea of nilpotent. 14. On 14, they give you a very specific Z to the Z6 homomorphism for this one. Think about if there's anything special about the Z and the Z6 or what's actually going on with the homomorphism. I mean, you can prove it for what it says for the homework. That's fine. But think if there's something special going on that doesn't require the specific rings, is what I'm saying. Okay. And then what else do I want you to do? I got a lot of ones that I've marked, but I don't want you to do all of them. 34. I think that's enough. Yeah. I might give you some more for practice for later, but I think that's enough for what I want you to turn in. All right.